In this video, we're going to talk about Chapter 6, which is on probability distributions. This chapter is going to build off of our last chapter, which talks about probability in sort of a wholeness sense. Now we're going to get into the specific types of probability models that we're going to use. So at the end of the last chapter, last section, I talked about probability models and how they approximate reality. In this chapter, we're going to learn about specific ones that approximate different situations that we're going to learn a lot about, or that we're going to use constantly in this course. So, as an outline, we're going to start off by summarizing possible outcomes and their probabilities. So again, this is sort of what we did in that last chapter, but we're going to have a different sort of flair or different flavor to it. And then, not in this video or this week, but next week we're going to talk about the normal distribution, which is probably the most commonly used probability model out there, and probably a close second, the binomial distribution. So we'll talk about what those are, their properties, how they approximate reality, so on and so forth, next week. So in order to talk about probability distributions, I need to define a new term to us that's going to take what we did in the last chapter and flip it ever so slightly. So, and that term is a random variable. So a random variable is a numeric measurement of the outcome of a random phenomena. So the last chapter we talked a lot about random phenomena, what they are, which is an event that I don't know the outcome to until after it happens. So I can't predict the outcome for sure. Okay? It's not predetermined. So that is a random phenomena, and a random variable is a measurement of that outcome of a random phenomena. And so we'll see what that looks like and how that's different from what we sort of did in the last chapter. The randomness often results, so the randomness of the random phenomena often results from the use of random sampling, which we talked about in Chapter 4, or a random experiment to gather data, also Chapter 4. Random variables help encode the probabilities that we talked about in Chapter 5. So, and I'm eventually getting to this numerical measurement of the outcome of random phenomena, the thing I mentioned in the very first point, okay, I'm getting to right here at the end. We'll use capital letters at the end of the alphabet to denote random variables, and their lowercase counterpart will denote a specific instance or realization of that random variable. So let's see what an example looks like. So if we have capital X, which is our random variable, it represents, or I define it to represent, the number of heads in 3 flips of a coin. So my random phenomena is flipping a coin 3 times. The random variable is only interested in counting the number of heads in those 3 flips. So I have the overall random phenomena of flipping a coin. A random variable is looking at a numerical measurement of some characteristic of that random phenomena. So the random variable would be the number of heads in the 3 flips. That's my sort of theoretical random variable. The lowercase counterpart, lowercase x, is that specific instance of when I get 2 heads out of 3 flips. So that's just an example. I could get 0, 1, 2, or 3, right? But x is what actually happened. Capital X is the theoretical counterpart of counting the number of heads in 3 flips. So the collection of all possible outcomes of a random variable and their associated probability that that outcome happens is called a probability distribution. And probability distributions are going to be sort of central to what we do in this course. So they're really important. So let's define different types of random variables. The first one that we'll talk about a great deal is called a discrete random variable. It's a random variable that takes on a set of separate values, and those could be 0, 1, 2, 3, 4, whatever. They don't necessarily need to be whole numbers. They can be points, but you can think of discrete random variables as describing categorical variables. So you would use a discrete random variable in a case where you have categories or a categorical variable, or of course a discrete variable, like we talked about in those earlier chapters. So when you have a discrete random variable, the probability distribution of a discrete random variable assigns a probability to each possible value of each possible outcome of that random variable. Okay, so there are a few sort of conditions that need to be met for these probabilities. Each probability has to be between 0 and 1. I can't have a probability of less than 0 or greater than 1. Okay? And if you don't like the 0-1 scale, you can think 0 to 100%. Okay? You multiply a decimal by 100 to get the percent equivalent. Oh, I'm sorry, by 100. And the probabilities in this probability distribution must sum or add up to 1. Okay? So each probability has to be between 0 and 1, and they must sum to 1. If my probability distribution describes all possible outcomes, then if I add up their probabilities, it has to include everything, which is 1. Okay? So the probability that I see anything happen is for sure, or 1, or 100%, whatever you want to think of it as. So, for example, if I have a random variable, x, that counts the number of dots on a face of one roll of a six-sided die, six-sided die that has 1, 2, 3, 4, 5, and 6 on its 6 sides. Okay? X is counting whatever comes up on that face that points up on a dice. So here is the probability distribution of that random variable. Okay, so X is the face of the die that I roll. The possible outcomes are 1, 2, 3, 4, 5, or 6. And so I write them all down. And then it has that, but it also has the probability that each of those happen. And so for a fair die, the probability that I see any head, any one of the 6 possible outcomes is 1/6. Okay? And so if you look at that second row down, that's the probability of each outcome happening. You'll see that each of those 1/6 6 times, each of those are between 0 and 1, and if you sum them all up, they equal 1. Okay, so that's important. So it matches what a probability distribution must be. You'll have examples in the future where you have to build a probability distribution, okay, and write those probabilities down. And as a check for yourself, you should look and see if each of them are between 0 and 1 and that they sum to 1. Because if they don't, then you know something went wrong. So, as an example, or as a little bit more on this, the collection of probabilities, that second row, has a specific name associated with it. And that name is called a probability mass function. Okay, so in a sense, it's a function. You have inputs, which are x, and it outputs something, which is the probability that you see that specific x. Okay, so it's a function. It's called the probability mass function, or PMF. So, it means PMF because you can think of each point 1, 2, 3, 4, 5, or 6 as a excuse me, as a mass. Okay, Anywhere else, like 1.5 or 2.4 or 3.3, there is no probability at that point. Okay? So I can't roll a 1.5, or I can't roll a 4.1, okay? Or I can't roll a -2. I can only roll those 6 things. And so there are what are called point masses at those specific points, hence why it's called a probability mass function. Okay, so that's enough with that. It's also common to be interested in the quantities, and I write it here in probability form, the probability that x is less than or equal to x. Okay? This quantity that we're interested in is called a cumulative distribution function, because I'm accumulating probabilities that are less than or equal to some point. So, for instance, I could be interested in finding the probability that I roll at most a 3. Okay, so I could be interested in the probability of rolling just a 3. That would be the first situation. But if I'm interested in the probability of rolling at least a 3 or at most a 3, at most a 3 would be 3 or less, then I would use something called a cumulative distribution function to find my answer, or look at to describe what I'm doing. So that's what this is, a CDF, okay, and you see it here. It is the third line down. Okay, so in the first line of my table-ish thing here, I have the outcomes of the random variable. Second line is my probability mass function, PMF. It tells me the probability at a specific point. And then the third line is the cumulative distribution function. It tells me the probability that x is less than or equal to some specific value. And you'll notice in this table that if you look at any specific instance along this row of the numbers, so for instance at 3 it's 3/6, okay, or 1/2, okay, you can find that number by going up to the second row and then adding everything at that point and to the left of it. So 3/6 is 1/6 plus 1/6 plus 1/6. Okay, and so the third row in this table is found by adding up everything at or before it in the next row up. Okay, you'll notice that the first number in the CDF is the same as the first number in the PMF, and the last number will always be 1, okay, because it needs to add up to 1. So here's a your turn. Okay, it's this same probability mass function. Okay, 1/6 all the way, and then the same CDF. So we're talking about rolling a fair dice here. I want you to find the following probabilities. Okay, the probability of rolling a 2, then a 2 or a 4, at most a 3, at least a 4, and then rolling a 3.5. So some of them will involve a PMF, some of them will involve the CDF, and then some of them are a bit tricky. Remember, probability only happens at the specific points or at the specific outcomes listed above. Okay, so I'll leave it at that and leave you to work on this your turn.